Okay, so I hope y'all are excited because I'm excited. This is a very natural place to start talking about differential equations, finally, right? We've talked all semester about linear algebra so far, and I kept telling you, well, we're going to apply this to linear differential equations. Now's our chance. We're starting now. This video is sort of an intro to linear differential equations, and I think it's pretty appropriate at that point at the introductory stage to ask basically three questions. First of all, what's a differential equation? What's a linear differential equation as opposed to other kinds of differential equations? And then maybe the most important, why do we care about these things in the first place? So I'm going to handle that last question first. It's just a basic fact of the universe that the entire universe is essentially governed by differential equations. This is how physics works. Most of those that we can understand, and certainly most of the ones that we can solve, happen to be linear. So let's do one quick example. Hooke's law says that if you have a spring, right, when you pull on a spring, it pulls back. But in fact, the pull back on the spring is proportional to how far you've extended the spring. So if we let x denote the position, that is how far the spring is extended, we can write down the following equation. Okay, so let's figure out in this equation what each term means. So I've labeled each element of this equation, as you can see, and this is basically just Newton's law, right? Newton says that force is mass times acceleration. So on the left-hand side, you've got the force coming from the spring. On the right-hand side, you've got the statement that that's proportional to the position, how much of the spring is extended. That's a great equation to write down. You can see it's a differential equation in the variable x. We're trying to solve for x as a function of t. We want to know where the spring is at each time t. And you can see it involves second derivatives of x. So maybe to make this a little bit easier to work into a framework, I want to rewrite this equation. So if we rewrite it with just a 0 on the right-hand side, that sort of should be familiar to us from algebra, right? You sort of always want to make sure you got the variables on one side and everything else on the other. In this case, the everything else happens to be 0, which means that this is a homogeneous system. That's all well and good, but sometimes there are other external forces involved, right? So we've written down here the only force involved is the spring itself. Let's say we attached a little rocket motor and had it just blast off at certain intervals to the end of the spring. What would happen? Well, that's going to exert another force in the system. So we could rewrite that in the following way. So that's the non-homogeneous version. This f of t is the external force, right? So it's a function of t, and it has nothing to do with x. It doesn't care about the position. It's just occasionally blasting off for no apparent reason. Okay, so you can see we can either have homogeneous or non-homogeneous ones. Roughly speaking, you can see we're going to develop a differential equation involving a second derivative anytime there's force involved, right? So that's a very large class of differential equations just come out of the fact that Newton said that force is mass times acceleration. There's many other examples, but I'll leave it to you to read about them rather than listening to me ramble about them. Okay, so how are we actually going to solve these things? Let's say we have a differential equation like the one given from Hooke's law. What's our approach going to be? So there's basically 4 steps here. The first one is going to be to rewrite the differential equations in the form L of y equals f. So here, L of y is what's called a linear transformation or a linear operator. It's going to take in a function and spit out a function in a linear way. We know what that means. And then the right-hand side, f, is going to have all of our t dependency. So it's not going to have any y dependency. There's no y's allowed on the right-hand side, but they can depend on t, so they can change over time. Then we're going to form what's called the associated homogeneous problem, and that's just you take f and turn it to 0. Okay, so it's a different differential equation. One has a 0 on the right, one has something else on the right. And the point is that's a homogeneous differential equation. It's a homogeneous linear equation if we're thinking about the vector space of differentiable functions. So its solution should form a vector space. Then we're going to find a basis. So each of these y1 through yn's, they are themselves functions that satisfy the associated homogeneous problem. Then we're going to go back to the original non-homogeneous problem, Ly equals f, and we're going to find a particular solution to that. Sometimes finding that solution is just making an educated guess, okay? Once we have that y sub p, though, we know from general theory, from linear algebra that we've already studied, that we can actually write down any solution to the non-homogeneous problem in the following form. So that is to say, we can write down any solution of the original problem that we want to solve as a linear combination of the y1 through y sub n plus this particular solution that we maybe just guessed or someone happened to tell us, we memorized, something like that. And that will give us actually all of the solutions. I want to point something out about this overall approach, which is that, the only calculus that we actually have to do here is like in step 3, right? The finding a particular solution. The rest of it is really just linear algebra. And I say, just in scare quotes because linear algebra isn't trivial, but we already know how to do it. That's how we're going to solve linear differential equations. Obviously, there's a lot of details. That's what the rest of chapter 8 is about, but here's how we're going to do it.